I'm Daniel, a co-author of this paper titled Evolving Fuzzy System Applied to Battery Charge Capacity Prediction for Fault Prognostics. I will introduce the topic and provide the motivations for the research in the area. Our method is an evolving fuzzy data-driven method. We use Takagi-Sugeno representation for multiple step ahead prediction and prognostics. We provide the method to propagate uncertainty through the evolving fuzzy system and have confidence bounds also as outputs. Our application example concerns the prediction of the charge capacity of batteries. The motivation is to, the objective is to improve the reliability, safety, and quality of service of systems. We want also to reduce the maintenance costs by means of condition-based maintenance, which is a period of time between preventive and corrective maintenance when fault symptoms can be observed. And we want to do that by means of an evolving fuzzy model and method. In fault prognostics, we have raw signals in the time domain like this. It is hard to find spatial temporal patterns looking to the time domain. So we extract features. These features are called health indices. The health indices generally tell the story better, tells when a fault is in the process of development. There are multiple stages related to the health of a system or machine or component. In the red stage, you see that clearly the health index is changing faster. So what we want is that in this last red triangle, we have a model that will estimate multiple steps ahead the point of functional failure of the system. So what we call remaining useful life of a system is exactly the number of time steps until a functional failure occurs. In prognostics, it's also important to have such Gaussian, such notion of uncertainty related to the estimate. There are two main lines of research in rule prediction: physics-based and data-driven based methods. In physics-based, we try to find relations, for example, electrical, mechanical, chemical relations that describe the system. When the systems are more complex, non-linear, and non-stationary, it is very hard to find such relations. So usually data-driven methods are considered. In this case, we have data sets to train models from the data. They are good in the sense that they are generalizable for different components and systems, and they don't need such complex relations of physics-based methods. There are some critics related to the physical meaning of parameters and the need of high-quality data. Within data-driven methods, there are the statistical and artificial intelligence approach. In the statistical approach, the data are fit into probability density functions. The point, a drawback of this is that in prognostics, we generally have multiple degradation stages of machines or systems, and such probability distribution is not sufficient many times for such model to be a model of such multi-stage phenomenon. So artificial intelligence methods gives input-output maps, which can be nonlinear. Sometimes when we use fuzzy systems, especially in the case of this paper, we have local models with a level of abstraction. We have a level of interpretability of the local models if we associate linguistic values to membership functions. So this is the approach we choose. with evolving fuzzy systems, we want to mitigate the disadvantages of all the other approaches I've just mentioned, such as the need of large data sets. We want to learn from data streams autonomously without storing the data. We avoid single stage degradation models. We have some level of interpretability. We can reuse the model in different units or components. And we have a method to represent, quantify, and propagate uncertainty through evolving fuzzy systems. We start with a typical TS fuzzy system with, in particular, a multivariate membership function in the antecedent part. We use ellipsoidal geometry for the clusters. This is the activation degree of a rule. This is a linear algebraic function. We normalize the activation degree of the rules. The output of the TS fuzzy system is this. In the matrix form, this is the same thing. All here is conventional. The activation degree, the input, the coefficients of the linear functions of the consequent of TS rules, and the extended input vector. The parameters theta are obtained by means of recursive least squares, and the number of rules C is time varying. C changes over time, the model is evolving. We combine prognostics with EFS by means of starting with this equation, the rule equation. The remaining useful life of a component is this N. N is the number of time steps until the health index surpasses the threshold for failure. When that happens, we have N, so we have the rule. The input vector of an EFS is V. It's called V. It may contain actual and estimated entries. For example, when N equal 1, which means the failure will happen in the next time step, then we have all the values to compose the input vector. But if N is greater or equal to, then we need to compose the input vector with the prediction. No matter if it has actual or estimated values, we call it V anyway. So the evolving fuzzy system plays the role of this function F. It maps the inputs V into the n-step prediction of the health index. If we open F, we have the activation degree of V related to V, the coefficients of the TS system, and again V. V tilde means the extended V with the offset term. However, if V contains estimates, these estimates are random variables, and V is a random vector. Therefore, we replace the later equation by this equation. Instead of using V to calculate the activation degree of rules, we use Z, which is the expected value of V, and we add an error. This error is modeled as a normal distribution. This is white noise, zero mean, a variance. The variance must be estimated, and it is estimated by this equation, which depends on M. M is a recursive way to calculate variance, error minus estimated error squared. So we compute this recursively and get sigma. But this sigma is the one-step variance. We need the n-step variance. And for that, we use this equation where we, again, accumulate values multiple steps ahead, n steps ahead. C comes from the TS system, and lambda comes from the covariance matrix of V tilde, this way. Graphically, what we have done is this. We have a Gaussian at this time moment, so we accumulate standard deviations. We are interested in the Gaussian n steps ahead to have confidence bounds around the pointwise estimate. This is the remaining useful life of the system. Our data set comes from NASA, Ames Prognostic Center of Excellence. It is actually 4 data sets related to 4 lithium-ion batteries. The batteries were charged and discharged 170 times, and we noticed that the charge capacity reduces over time, as well as the health index for the 4 data sets. We use mean absolute percentage error and relative accuracy as performance indices. We use one of the battery as training data to start the evolving systems, and then 20 instances of the other 3 test batteries to start to customize the evolving system for that specific battery. We compared 4 approaches. The one that I have just presented, error-based evolving Takagi-Sugeno, evolving multivariate Gaussian, extend Takagi-Sugeno, and autoregressive moving average. EMG also uses ellipsoidal clusters. Extended Takagi-Sugeno uses univariate membership functions. Any pair battery method is, each pair is fed with a different input vector, an input vector which contains a different number of legs. There is an optimal number of legs in each case. So we solve this optimization problem for that. This is the main result. For the 3 test batteries, the 4 methods, we have different legs for each one. And we have 15 scenarios on the prognostic starts at different time instants from 20 to 100 for the test batteries. These are the relative accuracies, so the higher the better. To sum up, EBETS won 10 out of 15 competitions, EMG won 3 times, Extend Takagi-Sugeno and ARMA won once. Finally, this is an example of pointwise and granular prediction for each of the 4 methods. This is the degradation of the health index for a specific battery. In red, the estimation, in blue, the actual data, and in black, the enclosure. We are especially interested in the enclosure at this point, at 7%. So this is the Gaussian around the red dot, the prediction. So it works. In this case, EMG works too, a little bit worse than EBETS, but still good pointwise estimate. EXTS failed in this case. It needs more samples to start to adapt its parameters better to be able to track the degradation. And the ARMA gives a good pointwise estimate, but the confidence bounds fail. I have shown in this paper the effectiveness of the evolving fuzzy system for online condition monitoring. We deal with a multiple step ahead prediction problem, AMI fault prognostics. We provide a way to quantify and propagate uncertainties within evolving fuzzy systems to obtain confidence intervals around pointwise estimates. In the future, we will couple this framework for uncertainty quantification with other evolving fuzzy systems.